All right, we're going to finish chapter 2 today. And then next Tuesday, we'll do a review on chapters 1 and 2. And I always base my reviews upon the review document. So if you haven't looked at it yet, you should take a look at it. In fact, if I were you, I'd work some of the problems. And then on that day, you tell me if you're having any specific trouble with any of those problems or anything else for that matter. We'll get that stuff out of the way before I go into a general talk. And actually, I just go in and I picked out some of the problems in that review document that I think are representative, would be not repetitive, but would cover the topics that you might see on the exam. And we'll just run through those. And maybe while we're doing that, something will click and you'll remember that you had a problem with that. Okay, so let's turn this into a slideshow. There we go. There's a little bit of overlap. Just a reminder of what isotopes are. What are isotopes? Quiz time.
The same number of protons for different neutrons.
Right, they're the same element, so they have the same number of protons. But the two atoms are different atomic weights. Actually, the different mass numbers. We haven't talked about atomic weight yet. They're different mass numbers because of different numbers of neutrons. Okay. So sodium's an example here, right, where you have 11 protons and 23. In this one, 23 protons plus neutrons. And here you have an extra neutron. Generally speaking, the mix or the fraction of isotopes in any element, in naturally occurring element, usually weighted heavily toward just one isotope. There are a couple of exceptions. Most notably is chlorine. Chlorine is almost 50-50 between two isotopes. Okay, we talked about how to write the symbols, except this one leaves out two positions, the charge and the numbers of atoms. Okay, did we do this exercise? Right. This is just to see if we've got a good handle on things. If your isotope has 23 protons, has 23 protons and 28 neutrons, mass number should be easy, just add them together, right? 51. So that we're calling that A. Like when we write our symbol, this is the number of protons and this is the mass number. So that's 51 mass number. How about the element? What would you do to find the element? Take that number right there. Huh? Oh yeah, let's see. Let's look. You don't have to have it memorized.
No,
Right, just follow it along here. The 22 is titanium, 23 is vanadium. Okay. So that's going to be vanadium, and we write it like 23 and 51. And if it's neutral, you don't have to put anything there. You can put a 0 if you want, but it's understood if there's no charge, then it's neutral. Okay. Now we'll say a few things about chemical bonding. I should put these slides in, flip the order. I'd rather actually talk about ionic bonding first, because it seems to flow better if you talk about complete transfer of electrons first. We'll come back to this one. So for ionic bonding, you've got two or more atoms. We're going to keep it simple for now. Let's just say we have two atoms, and we have the potential for forming a bond. For ionic bonding, one of them is going to be a metal, and the other one's going to be a non-metal. So they come from let's see, if you've done the, have we looked at the periodic table yet? Hold on a second. No, we haven't. Well, take my word for it. Metal and a non-metal. The reason being that metals prefer to give up electrons when they approach some other atom, if the atom will accept. Non-metals accept electrons, metals give them up, usually. And when we're talking about ionic bonding, we're talking about a complete transfer of one or more electrons from one to the other. So, example, if you have sodium metal, that means solid, so that's our sodium metal, and you have chlorine gas, right? Chlorine's diatomic, so it's going to be like that, correct? And when you bring those close together, it really doesn't take much to get them started. They'll react. This is not balanced though, because we get a compound of sodium and chlorine, table salt, and let's see, we need two of those and we need two of these. But what happens is you get electrons transferred from sodium to chlorine, and then that produces ions. When you do that, the bonding is purely electrostatic. Right? It's just positive attracts negative. Now we got a special name. So this one is the cation, and this one's the anion. Just memorize them. I don't have any fancy, interesting stories about that one. Okay, so how do we form ions? Yeah.
I need to call my daycare.
Yeah, go ahead.
I'm sorry.
Take your call.
I'm sorry. It's important.
How do we form an ion? Let's see, what was sodium was 11, wasn't it? Yeah. Neutral sodium, any of the isotopes of sodium are going to have 11 protons. And if it's neutral, it will also have 11 electrons. So how do you form an ion from a neutral atom?
Shed an electron.
Yeah, you have to adjust the number of electrons, right? Can't mess with the protons or you got a different element, correct? So the balance is between protons and electrons, and you modify the number of electrons. So if this is going to be a positive one, what do you do to the electrons? Take one away. So this one will have 10 electrons and 11 protons, which gives you the balance, add them together, you get one positive one. Okay, so that's the ionic bond, complete transfer of electrons. Let's see. We'll stop at covalent bonds this time. Covalent bond is sharing of electrons. And this occurs when you have a nonmetal and a nonmetal. Since nonmetals tend to accept electrons, like I described before, they're both competing for the same electrons. So what they do is they compromise. They say, okay, I'll take electrons part of the time and you take them. It's like they're divorced, but they're still attached by their electrons. They have, they share electrons. Sometimes they share electrons equally between the two. Sometimes they don't. Sometimes one of them gets a bigger share than the other. A case where you would have equal sharing would be something like oxygen. How about oxygen? Right? Oxygen is diatomic. So you're going to have two oxygens. And then, of course, we have some lone pairs out here. We'll learn how to draw those later. This is called the Lewis dot structure. But since they're the same element, they're the same atoms with the same number of protons, their tug of war is evenly balanced. So you have electron density. If you draw kind of a electron density, it's going to be evenly distributed electrons with most of these in this area. Okay. If you have something that has a stronger attraction for electrons, like if you combine, let's see, hydrogen and fluorine, that's a covalent bond. Fluorine is very strongly attracting toward electrons. So if you draw this electron density, it would look more like that. So the electrons spend most of their time around fluorine, but it's still a covalent bond. Now, the thing we have to remember is that, like I said before, I hope, nature just does what it does. And this explanation, ionic versus covalent, is the way we wrap our minds around it. In fact, covalent bonds can run the full gamut of electron distribution between the two atoms. If it's like this, we call that a polar bond, because you got more electron density over here and less over here. So what it does is it tends to be slightly negative on that side and slightly positive on that side. That's what that Greek delta means, slight, not complete. If it were complete like the ions, we just put a negative charge there. But when you do this, that means that it's not complete transfer. Okay, so the covalent bond is, in a nutshell, sharing electrons between two atoms. And in many cases, that's perfectly fine with those atoms. They get along fine. We're gonna talk about theories for explaining why that happens later. But it satisfies conditions for a bond.
So this is a video that addresses the question that students often have: what is the difference between a formula unit and a molecular formula? And that brings up a couple of questions itself. What are the structural differences between ionic and molecular compounds? And how do those differences affect their chemical formulas? So the chemical formula for a covalent compound is a molecular formula. And the chemical formula for an ionic compound is called a formula unit. So an example of a molecular formula, H2O, which is water, and for a formula unit, NaCl, the formula unit of common table salt. So what's the diff? And if we look at the structure visually, I think we can see very much what the difference is. So let's first look at sodium chloride. This will be our example ionic compound. NaCl does not exist as a single unit like a molecule, and this goes for all ionic compounds. So this would not be a valid way to represent sodium chloride. And like any ionic compound, in the solid state, sodium chloride exists as a crystal. So a very, 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 very tiny crystal would look like this with alternating sodium and chloride, and a little bit of a different view. The formula unit is NaCl, but if we look inside the crystal, the sodium and chloride ions are actually bonded to 6 oppositely charged neighbors. So if we shrink the ions, we can take a better look inside. And it's a little bit hard to see. So what we're going to do is take a look at a particular chloride ion, that one right there, and ask the question, how many sodium ions is the chloride ion close enough to bond with? Let's start with the head-on view first. And as we change the perspective, you can see there are exactly 6 sodium ions that the chloride ions is equidistant and can bond to. If we ask the same question of sodium, how many chloride ions can it bond to? Well, again, there are 6 chloride ions that it's equidistant to, and therefore the sodium ion also bonds to 6 chloride ions. So as you go throughout the crystal, you can see that is always the case. Because each sodium is bonded to more than one chloride ion and each chloride ion is bonded to more than one sodium ion, then you can think of all the ions in the whole crystal part of one single bonded unit. And the crystal below would be Na32Cl32. So you can imagine that would be very impractical given the enormous numbers of ions in a crystal large enough to see with our eyes. So only the ratio of ions is given, and that would be its empirical formula. But we call the empirical formula of an ionic compound the formula unit. And sodium chloride is the formula unit for the sodium chloride crystal, and it is the smallest whole number ratio of sodium and chloride ions in the crystal. So all formula units are the smallest whole number ratio of the ions in the crystal. That goes for all formula units. Here's another example, calcium fluoride. You've got 1 calcium for every 2 fluorides. The calcium is 2 plus, the fluoride is 1 minus. It has a slightly different crystal structure to account for, rather than the 1-to-1 ratio of sodium chloride, you have a 1-to-2 ratio of calcium fluoride. And if we shrink the atoms to take a better look and see how the calcium is connected to the fluorides, you can see that each calcium has 8 nearest fluoride neighbors, and so it is equally bonded to those 8 fluoride neighbors. And if we look at the fluorine, each fluoride has 4 closest calcium neighbors. And again, like sodium chloride, the whole crystal acts as one single bonded unit, and so we need to express the formula as the lowest whole number ratio, being CaF2. So what about molecules? How are they different? Let's take a look at water. We've got the space filling model on the left, ball and stick model on the right. It's covalently bonded hydrogen and oxygen. And a collection of water molecules is just that, a collection of individual units of H2O that are covalently bonded single units of 2 hydrogens and 1 oxygen. They're not connected to each other except by weak forces. And so large amounts of H2O, any attraction between the water molecules due to weak forces, the molecules they still behave as individual units, not one large bonded unit as in an ionic crystal. Another view of water, here the hydrogens are white instead of yellow. And this I'm showing you to contrast more specifically with the sodium chloride or the calcium fluoride, because we showed the ionic crystals as solids, and here's water as a solid, ice of course. And here, like ionic compounds, molecular compounds also form crystals in the solid state, a very ordered structure that you can see here. If we take a closer look, however, we can see that each H2O remains as a single unit and is not covalently bonded to any other H2O. The attractions that hold them in place are, of course, the very, very strong dipole, the hydrogen bonding, that occurs between the hydrogen and the oxygen. But that is much, much, much weaker than the covalent bond between the hydrogen and the oxygen, and the H2O therefore remains a single unit. So we look at these structural differences between molecules and ionic compounds by how we express them in their formulas. The molecule is represented by a molecular formula showing all the atoms present in the unit. The ionic compound is represented by the ratio of its ions, and that is called a formula unit. So here's the H2O molecule, and here versus the NaCl formula unit. Many sodiums and many chlorides, yet it's still just expressed as the lowest whole number ratio. It's 1 sodium to 1 chloride. In summary, in a molecule, the atoms given by the formula are all covalently bonded. In a collection of those molecules are attracted to each other by weak forces, but no covalent bonds occur between the molecules. The molecules exist as individual units of covalently bonded atoms. But in an ionic compound, where the bond is the electrostatic attraction between oppositely charged ions, each ion is bonded to each of its oppositely charged neighbors. So for any ionic compound, all the ions in the whole crystal can be thought of as part of one single bonded unit. So the formula unit shows the lowest whole number ratio of the ions, rather than representing very awkwardly all the ions in the crystal, which in most cases would be impossible to determine anyway. So that is the difference between a formula unit and a molecular formula.
Okay, let's see, what do we have here? We've got another problem. We've got an element that's got a single positive charge. And we're told it has 54 electrons. Okay, plus 78 neutrons. So what's the mass number? You can't just add these two together because it's not neutral, right? So you got to figure out how many protons do you have. Well, you should have one more proton than you do electrons, correct? So we should have 55 here. What does that mean? 133 is equal to the mass number. There we go. 53. So what element is that? Okay, we come. Is that right? No, 55, excuse me. 55. So we come back over here, cesium. So what we have is a cesium ion. Okay,
So all you did was just add another electron.
right, to compensate for that positive charge.
Okay.
It's positive because we've got one more proton than we do electrons.
Okay.
All right. So, we're going to see which ones of Dalton's statements are true. Still true today. All right. Dalton said that elements are made of tiny particles called atoms. Is that still true? Yep. Yep. Still true. All atoms of a given element are identical. No. Sorry, John. There are isotopes. Now, chemically speaking, they're very similar in the way they react. In fact, so similar, chemists can usually ignore them, ignore the isotopic scatter. A given compound always has the same relative numbers and types of atoms. Yep, that's true. That satisfies, let's see, which one was it? The law of definite proportions. You always have the same number and type of elements in a compound, no matter what the origin. Atoms are indestructible. I think we know now that with the discovery of radioactivity, fission in particular, we know that atoms are not indestructible. So those two are still true. All right, so the periodic table is subdivided there are some major divisions that help you organize what you're seeing in a periodic table. And first is the division between metals and nonmetals. Let's see, do we have the next slide of periodic table? All right, let's move on to the next slide. And we'll look at metals, nonmetals, groups, and periods. All right, so this black line is the line between metals over here and nonmetals over there. So most of the elements in the periodic chart are metals. And they share certain common characteristics. Like you can polish them to a shine. They're all but one is solid. Which one is not solid at room temperature? Mercury, there you go. Which one is solid at room temperature but will melt very easily?
Gallium.
Gallium, right. Just drop it in your hand and you get a puddle. Okay, so most are solids, but the nonmetals can be any one of those. Some of them are gas, some of them are liquid, some of them are solid. And this is the dividing line. Only it's not a perfect dividing line. It's the best we can come up with. What we noticed is that there are several elements that are right close to that line on either side. Sometimes they act like metals and sometimes they act like nonmetals. So they're called metalloids. Silicon's one, germanium, arsenic, antimony. And they're instrumental in advancing semiconductor industry. Silicon, in fact, is the basis of our semiconductor industry in the consumer market. Right? There are specialty semiconductors that are based on other elements, but they're extremely expensive, and you only use them when you have to. Okay, so now we have the major subdivision. We also have groups, and the groups are vertical in the way the periodic chart is arranged now. These groups have elements in them that are similar in chemical behavior. They're not exactly the same, but they're very similar. And there's a reason for that. We'll get to that eventually. And they have names. Some of these groups have names, probably grandfathered in from ancient times. These, of course, are the noble gases. These are the halogens. Right? Everybody's got, well, we used to have halogen lamps in our headlights in our cars. Now more and more they're LEDs. I think mine is still halogen. It's old enough. And this oxygen group, they're called the calcagens, based upon the description of many elements as calxes when they react. React with oxygen, you end up with a calx. It's basically an oxide of that element. And these are pnictogens. The nitrogen group starts with a P actually, but the P is silent. And then these are alkaline metals, right? Except for hydrogen. We only stick hydrogen over there for balance, right? It just wouldn't look right if we put hydrogen over here next to helium. In fact, it doesn't behave like any of these. I mean, it's like it's an animal unto itself. Alkaline metals, these are alkaline earths. And this whole group right in here is transition. Sometimes it's transition metals, sometimes transition elements. But these two groups plus all of these over here are known as representative elements. So the transition elements bridge the gap between representatives. And we have a couple of rows pulled out here. The lanthanides are named that because the first element in that group is this lanthanide. Notice it jumps from 57 to 72. That's because we pulled these out of that crack, put them down here. And we did that primarily just to make the table more compact. I mean, if we stuck them in there where they were supposed to be, the table would be as long as this wall. Well, maybe not that long, but it would be unwieldy. So we pulled those out, and then we pulled the actinides out also next to actinium that goes in that crack right there. And those are the only names that are given to groups. Next, we have periods. The rows are called periods. And they're called periods because and I find the relationship between this period and physics easier to remember. If you've ever had physics, you know about periodic motion. When you hear periodic motion, just think pendulum. The object moves through a cycle of some kind and it ends up back where it started. That's a period. Right? So when we go from left to right, we're increasing atomic number. Right? And then we get down to here, and if we go one more past that, it actually behaves like this one. So you just stop there and you start all over again. So that's a period. Okay. So another thing to notice about the periodic table is some of these groups, when they react, especially ionic compounds, when they react, they have a fixed charge. In other words, either accept or they give up the same number of electrons every time. The alkaline metals, that first group, is like that. They're always +1 charge. The second group, the alkaline earths, they're always 2+ charge. And that really simplifies things. I mean, if that's the only possible charge, you don't have to worry about what they're going to do when they react. They always form that charge. Halogens on the other end of the table, they always form a 1- charge when they react and form ionic compounds. Remember, nonmetals can form covalent compounds. So when they form covalent compounds, then all bets are off, except for fluorine. Fluorine is always -1, no matter what. Whether it's, well, if it's an ionic compound, of course, it's a full minus charge. But then I have to introduce a topic that we haven't discussed yet. If we talk about covalent compounds, it's called valence. So we'll get to valence eventually. But for now, and for naming compounds, when we start talking about them in a few minutes, think of these things in terms of charge first, and then we'll get to valence later. Noble gases, of course, they don't form a charge. They don't play well with anybody. They can be forced. We've got compounds of krypton and xenon with fluorine, but that's not what they prefer. They prefer to be loners. And we're going to find out why eventually. Okay, there's one group that was left off here. Let me back up. It's the boron group right here. Remember, +1, +2, +3. In ionic compounds, boron forms +3, aluminum +3, gallium +3. And in indium, I think, yeah, indium also. But when you get down in here, you have multiple charges. But down to that point, ionic compounds, they form +3 charge. Isn't that interesting? This one's a nonmetal, but it forms a +3 charge. And that one, aluminum's a metal. In fact, aluminum always is +3. You don't treat it as a metalloid ever. It's a metal, pure and simple. But its next door neighbor, silicon, behaves as a metal sometimes, as a non-metal other times. Okay, let's see. We also left out, now this is, again, this is ionic compounds. When oxygen forms an ionic compound, it's always a 2- charge. So if you go from left to right, you just say, start with this first column is +1, +2, over here +3. Notice we skipped the transition metals. That's good for good reason. We'll come back to those. And if we go over here to the right, we move from right to left, that's -1, oxygen's -2. Nitrogen would be -3 in an ionic compound. And carbon can flip either way. In an ionic compound, if it's combined with a metal, it behaves like an anion. It's a negative charge, -4. Okay, so let's move on. Now we're going to talk about naming compounds. So if we're going to name a compound, we're going to start off really simple. And we're going to follow the convention that is laid out and dictated actually by this organization. That's an acronym for International Union of Pure and Applied Chemists. One of their committees is dedicated to naming conventions for compounds. So whatever they decide goes. Now this is for primarily inorganic chemistry. Some of it bleeds over into organic, but organics, they sort of have their own bailiwick too. And then when you get to biochemistry, they have another set of rules. So we're starting really simple. We're going to start with binary ionic compounds, which would be a metal and a non-metal, just like this. Then we're going to use the rules that we learned from here to help us construct some new rules for naming covalent compounds. So we're sort of going to borrow from the rules here and name these compounds in a similar fashion, but not exactly the same. So we got 3 types. The first 2 types are ionic. Type 1 and type 2. Type 3 is covalent. So let's get into the meat here. Type 1 compounds. Over here. Type 1 compounds are always metals and nonmetals. And the metal has a fixed charge. So that means it has to come from one of those places on the periodic table. Alkaline metals, alkaline earths, boron group, in order to have a fixed charge. Those elements don't have any other charge in ionic compounds. It's always either +1, +2, +3. So once you know that, then you name the metal first, followed by the nonmetal. Okay, so skip one. Skipped a lot. Come on, get back there. There we go. So, for example, let's go back to our really simple one, sodium chloride. I named that first. Sodium is the metal. Sodium. And then chlorine, you change the ending to IDE. Okay. Metal, nonmetal, cation followed by the anion. Okay. So what's another one? Let's say, what if I wrote this compound? Like that. First of all, is that correct? That's a halogen, right? So it's a -1. This is an alkaline earth, so it's always 2 pluses. So that means if this is a -1 and that's a 2+, compounds have to be neutral. You got to balance the charges. So that's a total of 2 minuses, balances those 2 pluses. So yeah, it's written correctly. So how would we name it? Well, the metal came first, then the nonmetal. So this one, you just call it what it is. Magnesium. And then chlorine becomes chloride, just like this one. Okay? Yep.
Wouldn't it be magnesium trichloride since there's 2?
That would be redundant. One thing that the naming convention from that group is, one overriding rule is that the name and the compound are like they're joined at the hip. When you know one, the other one can't be anything but that. And they shy away from redundancy. We don't need to say dichloride because we know this one is a 2+ charge, that's a -1 charge. So we know the ratio based upon the charge. We don't have to say dichloride. Okay. Let's see, what's another one? How about this one? Let's see. Let me give you the name and you write the compound. About that. So calcium is what? Ca, correct? Oxide would be oxygen. So calcium is an alkaline earth, which is 2+ charge. Right over here. In the second column, second group. So we know that one has to be a 2+ and nothing else. Oxygen is a calcagen, which is always 2-. Charges are balanced. Right. Just 1 calcium, 1 oxygen. Okay. Now, sometimes we make compounds, these binary compounds, out of groups of atoms that behave as a single ion. They're called polyatomics. And there's a whole list of them. Let me see. I think I've got them here somewhere. Yeah. Did I hand out polyatomics to you already? Okay, good. Okay, so the characteristic of the polyatomic is that it is covalently bound internally. And then the charge is common to that group of atoms, which means when it reacts like this, or when we put it in a compound like that, it acts as a single unit. You don't tear it apart. You don't mess with its composition. For instance, if we wrote, instead of oxide, we wrote calcium phosphate, right? Then you go to that table I gave you and look up phosphate, right? And you know that it's this with a 3- charge. And the charges on polyatomics are fixed. They never change. So that one's always a 3-, and we know that calcium is, 2+. Okay, so now we need to balance the charge. So how do you balance an odd with an even? In mathematics, we cross multiply. So we bring the 3 over here and the 2 over there. But since these can't be messed with internally, we have to put a parentheses around it because we need 2 of those groups, not 2 of those and 8 of those. We would not write this. That's not the same as this. So with polyatomics, you need parentheses if you need more than one of them. Okay. So this would be calcium phosphate. And we wouldn't have to say anything about the charge of calcium or anything about the numbers of phosphate because the charge tells you how many there are in that compound. Now, you don't have to have the charge up here. Once you write the name, or once you take the name and write the compound, you don't need the charge. I was just using that for bookkeeping purposes. So we would leave the charges off when you write the compound. And any polyatomic would be like that. All polyatomics have a fixed charge. So that's why I gave you that table. So you don't have to memorize all of them. Let's see. There's one in there. There's one polyatomic that's a cation. In this group, there's only one cation. The rest of them are anions. So that one cation is ammonium. Right? So we could combine that with any one of the anions. And if we use this one, right, it has 3-, then this one is going to have to be 3 of those to balance the charge. 3 pluses, 3 minuses. Okay. So that's the case where you have a binary compound with 2 polyatomics in it. Okay, any questions so far? It just takes practice to follow the rules. Okay, that was a type 1. Type 2. The type 2s are also metal nonmetal. Except now, the metal can have a variable charge. Now that doesn't mean once you form the compound that the charge can change. Okay. Once it's in the compound, it's locked to a particular charge. It just means that when the compound is forming, it could be one of 2 or more different charges. You have to pick. Otherwise, the naming convention is the same, except for, since it's a variable charge, the name has to say what the charge is, because you can't deduce it from the, the name itself will not tell you the charge. The compound, if it's written correctly, will tell you the charge. So for instance, if we say this, right, rust, that's what that is. We know that the oxygen is a 2- charge because it's of the Calcagens group and it's an ionic compound, metal, non-metal. We know that this one's 2 minus, right? So how many minuses do we have over here? 6 minuses, right? So we got to balance that with 6 pluses over here. But there are only 2 irons, so we have, you have a question?
Oh, how'd you get 6?
6 here,
Yeah.
2 times 3,
Oh, okay.
that's 6 minuses for the anion. Okay. Like that. And then that means that this side, the cations, have to balance that to be a neutral compound. Which means if this is 6 plus, then what do we need up here to multiply by 2? We need 3 pluses, right? 2 times 3 plus is 6 plus. So now we know the charge on that iron. Now we can name it. So we just say iron oxide. And then we tell it what the charge is in the name. And the charge is in Roman numerals. Like that. Iron 3 oxide. Now, when I was going through the torture of my first chemistry class, there was a different convention. This would have been called Ferric Oxide from the Latin, ferro. Ferric oxide would have been 3 plus, and you just had to memorize it. If it were 2 plus, it would be ferrous oxide. And sometimes many of the supplements that you can find in the drugstore, they may still use that convention. I can read the label. It may say ferrous oxide or ferrous phosphate or something like that in the name. But now the convention set out by IUPAC is this type, which I think is more logical. Okay, let's see, that was compound to name. Let's see, go from name to compound. How about, let me see. Okay, how about this one? I don't even know if that's possible, but I just invented it. So 10 would be what? SN from stannum, Latin for 10. And this would be phosphite, which is PO3, 3 minus. Phosphate is PO4. This is phosphite. And this is going to have a 4 plus charge. So we got to balance charges, right? So this would be 4, and this would be 3. So SN3, PO4 3 taken 4 times would be the way you write that compound. Okay. I see some furrowed brows. At least I don't see any head spinning. That's good news. Do you have questions about that, or do you want to do it differently? I think we have some examples coming up. Yeah, well, those are type 1s. We've done type 1s to death. Let's go to type 2s. Here we go. So copper and bromine. Notice also that a great many of the type 2 metals come from the transition metals in here. But there are also some over here. Right? 10 is one of them that I just used. Some of those have multiple possible charges. But anytime you have possible multiple charges, you want to use the type 2 convention. And I think the periodic table I handed out, doesn't it have charges? Yeah, it has charges in it. So you can tell from that table whether you're dealing with more than one charge. Now, when you look at the nonmetals and you see a whole list of different charges, those are not necessarily charges. That was that topic I was talking about, the valences. So you use the convention from nonmetals and just let the compound tell you what their charge is. if it's not fixed, like halogens are -1, calcagens -2, pnictogens -3. Let's see, where am I going with that? Oh, there are a couple of elements in the transitions that are fixed charge. So they would be type 1s. Okay. Zinc is one of them. It's always 2+ charge. And silver, it's always 1+ charge. So if we had silver chloride, okay, 1+, 1-, that's it. You just call it silver chloride. You don't have to say silver 1 chloride. Or if we had zinc, if we had this one, that's it. Zinc sulfate. You don't have to say what the charge of zinc is, because this one is 2-, this one's 2+. So they balance with 1 each, this one and that one. Okay. Let's see. I showed you these already. So we should be good to go with those. That's the table I gave you. Notice on this side, it's got the exact same information as on this side. It's just sorted differently. This side is sorted by formula. This side is sorted by name. So if we had, let's see, PO4, 3-. If you add a hydrogen to that, think of hydrogen as a proton, it's a positive charge, then it would take out one of those negatives. This would be phosphate, this would be hydrogen phosphate. That's a polyatomic ion. Or this one would be 1-, dihydrogen phosphate. Polyatomic ion. Okay. So now we need to go to type 3s. Type 3s are actually the easier of the bunch. Type 3s pick up where your question was. You actually, in type 3s, you actually say how many of each one you have because they don't have a charge. So if you have something like, and it's always non-metal, and they're always covalent. So we kind of have to fudge a little bit from here to here because we can't use ions anymore. But we do try to put them in the same order. In other words, we put them in the same order as if this were a cation and this were an anion. But they're not really. So how do you know which one comes first? Well, as a general rule, the one that occupies the cation position is to the left on the periodic chart. So if we want to form a compound with carbon and oxygen, we put carbon first, like this one. You know, that's the one that you don't want to get trapped in your car in the garage with the motor running. That's carbon monoxide. We just say carbon, and then how many oxygens? And we use the IDE ending, just like we would with either one of those. Or the one that's supposed to be an existential threat to the planet. Carbon dioxide. And notice that there's only one carbon, but if it's in this position, if it's in the first position, in the metal position, the cation position, we never say mono. Mono is only used for the second one. Now, if it's di, of course, if it's two of them, you do say di. But it just, chemists can be aesthetic too. Right? It just doesn't sound right to say mono first. Monocarbon, monoxide. So carbon monoxide is all you need. What about let's see, let's go backwards. Let's try di-nitrogen tetroxide. Okay, we know we need nitrogen, right? We know we need oxygen. How many of each? We need 4 of these, and we need 2 of those. Okay. So the real trick to type 3 is trying to figure out which one comes first. Most of the time, it's the one to the left comes first, but not always. So the ones that are kind of outliers, you just have to memorize those. Okay. And these are all your prefixes, if you don't already know them. They're from the Greek: mono, di, tri, tetra, penta, hexa for 6, hepta, octa. Everybody knows octane rating for your gas. Right? That's where it comes from. Octa octane has 8 carbons in it. Nona and deca. That's as far as we're going. You can go beyond that, but we're not going to do it. Okay, so that's type 1, type 2, and type 3. Well, I did this one for you already. There's sulfur hexafluoride. Let's see if that follows the convention. Yep, sulfur's over here, fluorine's over there. So sulfur's to the left of fluorine. Let's see, nitrogen and oxygen, yeah. Carbon dioxide, okay. So those follow the convention. The one to the left occupies the cation position. Okay, and this is just a schematic for what do you do if you're faced with a compound that you have to name, or you're faced with a name that you have to write the compound for. You decide, is it a metal nonmetal or a nonmetal nonmetal? If it's a metal and a nonmetal, then you got to put it in the type 1, type 2 slot. If it's a nonmetal nonmetal, you put it in the type 3 and go ahead with it. Then, if it's in the type 1, type 2, you got to decide, is it a metal that's fixed charge? So you look at your periodic table, where does it come from? That'll tell you if it's fixed charge. And then, if it's not one of those, then you have to find out what the charge is. You have to deduce the charge, either from the name with a Roman numeral, or from the compound if you're going to name it, and find out what the charge is. Okay. Now, believe it or not, that binary naming convention was the easy part. Now we have to name acids. And acids are sort of grandfathered in from ancient times. What we've tried to do is standardize the naming convention. So here's what we've come up with. First of all, if you're asked to name an acid, you got to ask yourself, is it an acid? Right? That's how tricky some test questions are. They ask you, name this acid, and you look at it and say, that's not an acid. So it has no name. It has no acid name. So first of all, does it have hydrogen as the first element? Only acids always have hydrogen first. Now there's some non-acids that have hydrogen first, but it's got to have a hydrogen to be an acid. 1, 2, 3 usually, max, and then something else. And the hydrogen occupies the cation position. It's considered, it would be considered positive charge, and something behind it that's negative. Well, then you look to what's behind it. And then you say, is there an oxygen in there? Right? For this one, that's chlorine, there's no oxygen. For this one, let's see. Let's use that one. Okay, so there's a difference in naming conventions between these two because of that oxygen. And if it's got an oxygen in it, more than likely is a polyatomic ion anyway. So you got to look and see in your chart, what's the name of that polyatomic? Well, this one, first of all, let's name it with the convention that we know already. Right? So this would be hydrogen chloride, correct? What would this one be? NO3 is nitrate. So this would be hydrogen nitrate. The thing that makes them an acid is you dissolve them in water for our purposes. Right? Later down the road, we can investigate acids that are non-aqueous. But for now, if we want to make an acid out of that, we just put it in water. Okay, AQ means aqueous. Now the name changes. Now, if there's no oxygen there, we start the name with hydro. And then we take this part of the name from here, chloride, I becomes ic. So this is hydrochloric acid. Okay? That's only if there's no oxygen there. You name it that way. Right. We can do the same thing with this one. Right. Hydrofluoric acid. By the way, concentrated versions of hydrofluoric acid are very dangerous. They're not just dangerous because they're strong acid. Well, actually, this is not strong acid. This is dangerous because of the fluoride. If you get concentrated hydrofluoric acid on your skin, it'll eat right through to the other side. Fluorine likes minerals, so it goes after everything you got in your hand. Okay, hydrofluoric acid is usually dangerous only for its acidic properties. Okay, for this one, since it's got oxygen in it, you don't say hydro. You go to the anion part of the name, and then eights become X. Up here, I becomes dick. Here, 8 becomes dick. So it's nitric acid. That's all you have to say. We know from that name that it's this formula and it's in aqueous solution. Okay, let's try another one. How about this one? What's that polyatomic ion? Phosphate. So phosphate becomes, there's oxygen, so we don't say hydro. Phosphoric. Now that's not strictly speaking, 8 becomes ic. Phosphate becomes, it would be phosphic. if we follow that convention, and that just doesn't sound right. So we drag it out a little bit. Instead of saying phosphate, we say phosphoric. Sounds better. Okay, let's see. We're probably going to have some examples here to look at. Hydrochloric. Oh, here's a polyatomic that doesn't have any oxygen in it. The cyanide ion, Cn minus. Since it has no oxygen, we say hydro. Hydrocyanic acid. Now you have to assume that all of these are an aqueous solution, otherwise it doesn't make sense. And this one, okay, I'm going to draw a contrast between this one and this one. Okay, this one has no oxygen, so it's hydro. Sulfuric. acid. This one has an oxygen in it, so it's just sulfuric. Because that's sulfate, sulfuric acid. Okay. Let's see here. Where am I? Okay, the next is the flow chart. No, it's oxygens. Oh, here's a good one. Let's do this one. I'll just erase them all. We'll do it one time. I always have to check. Got 15 minutes. I better hurry up. So this one, C2H3O2, is obviously a polyatomic ion. So you look it up. C2H3O2 is acetate. Right? So that would be hydrogen acetate. Hydrogen acetate. Make it aqueous, it's acetic acid. Okay. 5% acetic acid is vinegar. So you probably doused your salad in oil and acetic acid. Now, this is interesting. Acetic acid can be made 100%. And if we do that, we would expect it to be named hydrogen acetate, but it's not. They start from this name, and instead of saying 100% acetic acid, they call it glacial. Glacial acetic acid is 100%. There's no water there. So, it's just one of those things that you have to memorize. Most acids, it's difficult to make them that concentrated. Sulfuric acid, you can get sulfuric acid up to 98%. Let's see, nitric acid, you can get higher than this, but I've never used it higher than 70%. And hydrochloric acid is even lower than that, usually about 35%. Okay. Let's see. So anytime you have oxygen in your acid, it's probably a polyatomic. All right, there's another decision chart, flow chart. Let me see, do I have time to talk about this? If we make it quick, are these named correctly? Which one is not named correctly? Right? That's a fixed charge. That's a fixed charge. So we only have to say potassium nitrate because that's +1, -1. Right? That's good right there. How about this one? Oxygen is 2-. So 2 times that is 4-, correct? That means titanium has to be 4+, which is wrong. Okay, so that's the bad one. These are still good. Hydroxide is -1. And 10 then would have to be +4 to match those scores. This is a type 3, so we just say phosphorus pentabromide. And this is a type 1 because calcium is from the second column, 2+ charge. Chromate is a 2- charge, so there's just one of each that does it. Let's see, I was going to say, bases. We didn't say anything about naming bases. Bases are simple. You just name the compound. And then if it's in solution, you say, like sodium hydroxide. Sodium hydroxide is that. We haven't said about what its phase is, what its form is. If we say this, we'll say sodium hydroxide. Sometimes it comes in flakes and sometimes in pellets. We just say sodium hydroxide solid and maybe say what it is. But if it's in solution, we say sodium hydroxide aqueous. And usually, you'll say the concentration also. The bases are really simple. They don't give you near as much trouble as acids do. Probably why there's no separate section in this discussion of bases. But they're just as dangerous. Concentrated forms of bases are extremely dangerous. And when you mix solutions with them, if you go from the concentrated acid to the concentrated base to a more dilute solution in water, you want to add small amounts of acid and base to a large amount of water because they're extremely exothermic heats of solution. And if you add base to water, water to base or water to acid, the heat of solution is sufficient to cause the water to boil almost instantly, which means spatters right back in your face. So that's why we say do as you ought to add acid to water. Okay, last one. Some compounds have water attached to them. And the water is separate and it's a distinct molecule in the crystal structure of the ionic compound. Okay, but it's always in there. Well, not always, but we can define it in terms of ratios of how much water is there per mole or per unit of formula unit of the compound. So in this case, zinc sulfate crystallizes with 7 waters per one of those units. Okay, so we know zinc sulfate looks like this, right? Zinc is a 2 plus, sulfur is a 2 minus, and we only have to say zinc sulfate. Why? Because it's fixed charge, like I said before. But it's going to have 7 waters with it. Now, we don't write the waters in here because these water molecules are entire entities. They're not mixed into that formula. They're in the crystal structure, but they're not part of this ionic compound. So we just put a dot right there. These are called waters of hydration. Okay. They're distinct water molecules in the crystal structure. And to name it, we name this first, and then we say how many of these hydrates. So this would be heptahydrate. And this would, of course, be zinc sulfate. And that's the complete name, zinc sulfate heptahydrate. Okay, we're going to do a lab this year where we're going to determine the ratio of waters of hydration to the molecule. We're going to use copper sulfate in that case. We're also going to look at other types of waters, waters of constitution. In that case, the water is part of the molecule. And you only know the water is there. Well, it's really not there, but it comes out as water when you heat it. Okay. We're going to use baking soda, sodium bicarbonate, sodium hydrogen carbonate. Okay, so I think that's the last slide. And the reason I stuck this slide in here is because we're going to do that lab. And if we do the lab without explaining what it is, then it's a little more difficult to understand. Okay, any questions?